This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to discuss using the porous material model in the Aries modeler. Before I get into the model itself, I need to discuss some of the effects that porous material has on acoustic processes. These are mainly divided into two areas: viscous effects and thermal effects. On this slide, I have a representation of air flowing into a small tube. Below, this is meant to be a cross-section of the velocity profile that you would see in that tube. Since this is an acoustic process, the velocity would be traveling back and forth. In fluid mechanics, there's a condition called no slip at a fluid wall boundary. So the assumption is that the fluid is not moving at the walls. Since we do have fluid motion inside of the tube, there will be a velocity gradient from the maximum velocity in the center of the tube to zero velocity at the wall. This velocity gradient causes a shearing of the fluid. Since air is essentially a compressible fluid, the viscosity of the air causes an energy loss mechanism or a damping mechanism as the sound travels through the small tube. This energy loss mechanism leads to sound attenuation or the resistance to airflow through the small pores. The smaller the tube, the more shearing you have, and so the more resistance or viscous losses you have as the sound travels through the tube. This viscous shearing of the fluid as it travels through the pore is the main cause for resistance when you try to blow air through a cloth, such as your shirt. This resistance to flow caused by the viscous shearing is one of the main energy loss mechanisms of sound traveling through porous materials. The next major effect is from thermal conduction of energy from the air into the walls or the porous material structure. When you compress air, that air will heat up. If that process is slow enough, there will be time for the heat from the air to conduct into the frame of the porous material. On this slide, I'm showing a volume on the left here with a plunger ready to compress the air in the volume. If at time equals 0, you suddenly push the plunger in a significant distance, the air inside of that volume will heat up. If the plunger is held in place for a relatively long period of time, the excess heat generated from compressing the fluid will have time to conduct out into the walls of the volume. As that heat energy conducts out, the pressure in that volume will slowly drop. This effect is roughly sketched here, where at time equals 0, the plunger is thrust in, and the pressure climbs to some value we'll call P1. As time progresses, the heat conducts into the walls of the volume, and the pressure will drop to a steady state value of P2. In the world of thermodynamics, P1 is referred to as the adiabatic pressure, whereas after the temperature has been allowed to equalize, P2 will be an isothermal pressure. Note that P2 is less than P1, so it's easier to compress gas isothermally than it is to compress it adiabatically. With an adiabatic compression, there's no time for any thermal transfer between the air and its surrounding environment. With an isothermal compression, the process is slow enough so that the air temperature remains constant. There are some important numbers to glean from this graph. First of all, P1 divided by P2 has a very specific value. It's called the ratio of specific heats. It's given the variable name gamma, and it's approximately equal to 1.4 for all simple gases. This means that if you compress the air slowly, it's 40% easier to compress the air isothermally than it is adiabatically. If you look at this graph, there's a time constant here, I'll refer to as tau. You can imagine that there's a slow decay from P1 to P2. 1 over tau will be a frequency, which we'll refer to as the thermal transition frequency. For a 1 millimeter diameter tube, the thermal transition frequency is about 150 hertz, so it's fairly low. But if that tube is decreased to just a quarter of a millimeter in diameter, the thermal transition frequency goes up very quickly to a value around 2.3 kilohertz. What you see here is a graph showing frequency on the X scale, and the Y scale shows the effective bulk modulus of the fluid. This is how hard it is to compress the fluid, how stiff that fluid is. At low frequencies, where we can expect the compressibility to be isothermal, the bulk modulus is the ambient pressure of the gas, or P naught. For us, this would be the atmospheric pressure, or 1 atmosphere, which is roughly equal to 0.1 megapascals. At higher frequencies, where the compressibility will behave adiabatically, the bulk modulus increases by a factor of gamma, the ratio of specific heats. So this is 40% stiffer. You can imagine that between the low frequency isothermal process and the high frequency adiabatic process, there will be a transition at the thermal transition frequency. As we move between these two extremes, the bulk modulus will actually become a complex value, indicating that the compression and the pressure are out of phase. And so this becomes another loss mechanism for sound in the porous material. So these are the two major effects of porous material on sound propagation. Viscous losses as the air shears between the port walls, and thermal conduction as the temperature equalizes with the porous material. ARES uses a simple porous material model that assumes that the porous material is comprised of a number of parallel tubes which may be bent at an angle, and so the air doesn't go straight through the tubes but follows a tortuous path. The three parameters that ARES uses in its model are the pore diameter, the porosity, and the tortuosity. The pore diameter is a somewhat fictitious diameter size of the individual pores in the porous material. Some materials have well-defined pores that you can identify. Others don't have anything that looks like a pore at all, but this model still effectively captures the behavior. Porosity is the fraction of the volume occupied by the air. So if the porosity is 0.9, that means there's 90% air and 10% solid material. Most of the materials we work with in acoustics have a very high porosity of 98 or 99%. It doesn't take much material to have a significant effect on the acoustic behavior. Tortuosity is a measure of how tortuous the path is as the sound travels through the material. A value of 1 roughly means that the air flows directly through the material. A value of 1.2 would mean that the air path is roughly 20% longer than the length that you'd measure if you just simply measured the distance through the porous material. The tortuosity mainly affects the viscous damping. So by setting the tortuosity value of 1.2, you're increasing the viscous damping by roughly 20%. To give you an idea of what some of these materials look like magnified, this is an example of an open cell foam. On the left, it's just a simple block of the material. On the right is a highly magnified view of what this foam would look like. Now this is an open cell foam, so the cells between the pores are completely opened. There are closed cell foams where these pores are skinned over with material. We don't want to use that. As you can see here, we might be able to identify an effective pore size fairly readily. On this next slide, I'm showing some polyester batting, which is typically used in speaker applications. Here's a magnified view of what some of this batting would look like. It's largely composed of individual strands of material layered over each other in random directions. As you can tell, it's pretty hard to identify any kind of definitive pore size, but the pore model that Aries uses is still surprisingly effective even on a material that has a structure like this. But identifying the pore size comes down to measuring the acoustic behavior of the material. It's hard to predict ahead of time. There are some important limitations of the porous material model that Aries is using. One of them is that the porous material doesn't move. This is also referred to as a rigid frame assumption. So as the sound travels through the material's pores, the material itself is massive enough or rigid enough not to move. This assumption is surprisingly true for most conditions. However, there will be some materials which will move at some kind of resonant frequency. This resonant frequency usually extends over only a short frequency range, and so even if we do get some material motion, it's usually not very significant for the overall acoustic behavior of the material. So leaving out the material motion allows us to dramatically simplify the model without losing much detail. Another assumption is that the pores are open or they're interconnected, so that when the air flows into the material, it's able to flow into all the pores, all the pockets, and when it flows out, all of those pores and pockets are evacuated. This model isn't appropriate for closed cell foams or for a material that might have an impervious skin over top of it. But it's usually undesirable to use these type of materials in acoustics anyway, so this shouldn't be a major limitation. One of the best uses for the porous material model is in predicting the effects of filling a volume or a port with a fibrous material such as polyester, which is typically used in a loudspeaker box. So that's a quick introduction to some of the theory behind the porous material model. I'm now going to open up Aries and build a quick little model to show you how you might be able to use this. So I've brought Aries up. I'm going to create a modeler module, and now I'm going to start building the model. I'm not going to put the elements on the top level model, however, because where you specify the porous material behavior is in global parameters. Under global parameters, you find the fluid properties that will be used for all the elements. There's an option to use a porous material model. If I click this, the porous material parameters become available, and all of the elements that uses the fluid will now use these porous material properties. Note that you'll usually only want to apply porous material to a few elements in your model. By selecting it here, all of the elements in our model will have the porous material applied to it, which is typically not what you want. So I'm going to turn this off, and instead what we're going to do is we're going to create a subcircuit. So go to Miscellaneous, create a subcircuit, and now I'm going to click inside of this subcircuit, and we can create a new model inside of here. I'm going to go ahead, go to the acoustical menu, select circular port. I'm going to set its size to be 50 millimeters long and have a diameter of 25 millimeters. These sizes are going to be important in another video, so I'm just going to select those for now. So I'm going to want to drive this tube at one end and leave the other end unconnected. When I leave the other end of this port unconnected, that means there's going to be an infinite impedance here, or velocity 0, at the node to the right. This effectively turns this port into a volume. But since a port takes the standing waves into account, we will see the effects of the standing waves inside of this volume. To bring this node out, I need to create a node element, and I'm going to connect it up to the left side of the port. I'm going to click on the node element, and I'm going to give it the name of port volume to let us know that it has it's connected to the volume. Now in this subcircuit, I can specify the fluid parameters just for this subcircuit. When you create a subcircuit, by default, it inherits the parent's fluid parameters. So the circuit that this subcircuit belongs to will be used for all the fluid parameters unless I turn this off. So by unchecking this, I can now specify the fluid parameters for this entire subcircuit. Now I'm going to turn the porous material model on, and so the porous material model will only be applied to this element, number 1 here. I'm going to stick with the default porous material parameters, which will be discussed in another video. To go back up to the main circuit, I'm going to right-click and select Move Up One Subcircuit Layer. And the subcircuit element now has port volume as the name of its node. I'm going to need to drive this, so I'm going to create a pressure element to drive it with. I'm also going to want to compare the impedance into that porous filled port with an identical port that's just filled with air. So I'm going to go ahead and create another port element in this upper circuit. I'm going to give it the same length, same diameter. I'm going to drive it as well. I'm going to solve for this. Actually, I'm going to go and increase the number of frequency points to 2000 so we have lots of resolution. I'm going to solve for it, so that solves pretty quickly. I'm going to create a graph element, and I'm going to first plot the impedance of this port. When I created the graph element, this graph window was created. Now right now it's showing 94 dB. That's because we're plotting pressure. So I want to select impedance instead, and I'm going to set the line weights to 3 so it's nice and heavy and we can see the impedance. So I'm going to go back to the graph element. And this is the impedance, and this is magnitude dB in acoustic ohms of the impedance. And this is the impedance seen looking into that air-filled port. It's 50 millimeters long. At low frequencies, the impedance is fairly high because it's behaving like a sealed volume. At the odd number of quarter wavelengths inside the tube, we have impedance minimas. At even number of quarter wavelengths, we have impedance maximas. So this is a largely undamped tube just filled with air, the impedance filled with air. I'm going to copy that into buffer A. I'm going to call it air filled. Press the A button to copy it. Hit that check mark so it'll be plotted. And now I'm going to move down to the subcircuit node and plot its impedance. So let me go back to that graph. So now the air-filled data has been copied into the A buffer, which is plotted in green here. And the impedance with the porous filled tube is shown in the blue curve. As we can tell immediately, the effects of the quarter wavelength and half wavelength resonances have been pretty much eliminated. There's a little bit of a wiggle here, but the porous material has dampened the resonance so much we barely see them. Another major effect, which is perhaps even more important for us, is that the impedance at low frequencies has dropped. This is the effect of the thermal conduction going from an adiabatic compressibility with the green curve to an isothermal compressibility at low frequencies due to the porous material. To take a little closer look at this, I'm going to go to the advanced graph options and plot the real and imaginary part of the impedance. I'm going to go back to the graph. So on the real and imaginary part, these resonances are dominating what's going on. I'm going to want to zoom in on this graph so that I can see the real and imaginary terms with the porous filled material as well. So the blue impedance is that filled with porous material. The imaginary part of the impedance at low frequencies has decreased. This is our 40% reduction in the impedance. Another way of looking at this is that the volume is behaving 40% larger due to the presence of the porous material. Also, the real part of impedance seen looking into that tube goes from virtually 0 to a finite value for the real part. And it continues to behave fairly well through the standing wave resonances of the tube. So this is the major effects of the porous material model that I wanted to show you. ARES is able to predict thermal effects, which are especially important at low frequencies. It's able to capture the viscous effects, which is largely responsible for the real part of the impedance. And it shows that these resonances virtually disappear when the volume is filled with the porous materials. So that's the majority of what I wanted to show you. ARES is able to model the most important effects of putting porous material in your design. I'm going to have another video showing how to obtain some of these parameters using the SEMA impedance measurement apparatus. Or if you'd like, you can always contact May and ask for some help in parameterizing any particular material that you're looking to use. Please feel free to contact us if you have any questions, and thank you for your time.